We live in very strange times. Very few times in history, I think, have affected so many people from cook to king as the coronavirus. And I was surprised to see very small children are now able to draw the coronavirus. In our days we were happy as children if we could draw an ugly tree or maybe a very simple house that nobody could build. But they can draw the coronavirus, a sphere with these red spikes on the outer surface on it. But if you look at the professionals, you could wonder, are they able to draw the coronavirus? Because if you look carefully in newspapers, magazines, on the news, somehow the virus always looks different. And I've even seen variants where the spikes were not red but blue. So what's going on? This is called an artist impression. Why do they do that? It's typical in science, because if you photograph the real thing, it's not always as perfect and it's chaotic, and you want to make a sketch of it which summarizes the essentials so that people can readily see what it's all about very quickly. Of course, a good artistic impression for science has to be 99% close to the actual truth, and only 1% artistic liberty, beauty, and so on. So something like the one here is also an artist impression, but of course nobody would believe that the virus consists of the moon and a strawberry. So what can we actually see? A first question to be clear is, one should ask, maybe a virus is too small to interact with light. Let's first see how big the virus is. I'd like to compare everything with a human hair. Now, a human hair can be thicker and thinner like everything. There is some variation, of course, but it is typically something like 15 micron. Now, a micron is 1,000th of a millimeter, which by itself is 1,000th of a meter. And a millimeter is also 1/25th of an inch for the American viewers. So 1,000th of a millimeter, that's already quite small, but we can go even smaller and divide it into 1,000 even smaller things, which are called nanometers, and they are 1/1,000,000th of this small millimeter. A millimeter is typically the size of a nail clipping, the width, not the length. Now, grass pollen, for example, so some pollen are again bigger and some are smaller, are about 25 micron, just like the droplets in a cloud. These things stay afloat, which is good for pollen, because then the plant can disperse its pollen and create new plants. And also in the cloud, of course, the droplets stay afloat until they bump together and become bigger and bigger, and then they rain on your head. Animal cells are typically, like this red blood cell for example, about 10 micron. So putting it on top of the hair, you would have about 7 of them on the width of a hair. And of course other cells can be a little bit smaller and so on. Then 10 times smaller we have our bacteria. They are about 1 micron. So you would have about 100 bacteria on the width of a human hair. And viruses are even 10 times smaller, so 100 times smaller than our cells, which is 1/10 of a micron or 100 nanometers. And then you have the really small things like the atoms or the DNA and the RNA. In virus it's RNA, and in our cells DNA. And then you have another interesting thing that people are learning about nowadays, the aerosols, which you know of course from your deodorant and the spray, that you spray these little droplets or little solid particles suspended in air. Now these aerosols can contain virus, because if you sneeze, for example, the bigger droplets can be 100 micron or 1/10 of a millimeter, and these thick droplets, they quickly fall to the ground or a table, where they're still dangerous because then they become fomites, and if you touch them you can put the virus in your eye or whatever. But the small ones, smaller than 5 micron, they tend to stay afloat in the air for up to hours, and you can also easily inhale them into your lungs. Here you have our nanoparticles. These are smaller than 100 nanometers, so for example soot, very small particles, or smoke and the like, and they can also be not so healthy if you inhale them. Another very well known one, asbestos, are these fibers which can be like 20 micron. And So now let's compare the virus with the wavelength of light. The shortest wavelengths are the blue light, and even these are about 4 times as big as the virus, which is bad news, because if something is smaller than the wavelength, it cannot be seen. That doesn't mean it cannot interact with light. Let's look at the blue sky. What happens there? Why do we see blue? The molecules in the air, and there's not much smaller than nitrogen and oxygen, they scatter the light, so the red and the green light keep going on largely untouched, which is why those together show us the yellow sun. But the blue light is scattered in all directions, so from all directions of the sky where you don't see the sun, we get blue. That's not red yet, but molecules can also sometimes absorb light and then become red, for example. So it's not that the virus couldn't interact, couldn't take away some of the light or emit locally some of the light, but the problem is it is too small to see structure in the virus. Because what is going on? Light likes to spread, just like if you have waves of water or even people squeezed together through a small hole, then after the hole it likes to spread. And that is what also happens with, if you take an image, you would typically use a lens, because otherwise you don't collect enough light and you have another problem. And that lens has a certain diameter. And that diameter determines, together with the focal length, but also together with the wavelength, how much the light is spread out in a blotch like this, the so-called point spread function. And if you take the diameter of the lens about the focal length, more or less, this more or less 1, then you see that this becomes bigger and bigger the more the wavelength of the light becomes bigger. And red had a very big wavelength. So actually the lens would image this red spike over here, but very close to it, it would image the body of the virus, and that would have other colors, and these would mix, and you wouldn't see structure, but also you wouldn't see the red color. It would mix to some mixture color. We can also see the problem a little bit as where it happens. Suppose you have a mosquito on the water, and it's super mosquito, and it can pound on the water like a Superman. Let's not dive into all the details of gravity versus other effects, but let's just say it creates waves. Then if it's much smaller than the wavelength, it will look like a point source. So it can use its right leg and it can use its left leg, and it can try to make something different, but it will all look as if it happened at one spot, which is very different from if you had, for example, an oil platform. If that could tap dance, this would be much bigger than the waves, and you would see here all kind of things, and there it could have different amplitude. And then the light coming from here to our eye, or our water wave eye, or from here, you would clearly see something different. But here it would all come as if it was a point source. So you can't see the internals of an object if it is smaller than the wavelength. For those of you who don't have a pond or a mosquito or an oil platform, you could see it a little bit simpler even with this ruler. Maybe some of you have made ruler music, so you block it at one side and then you can move it at the other side and it creates a wave. But the small mosquito can of course jump on it very strongly, and it can activate it and it can create waves, but it can only create this one single wave because it has only a very small isolated position. Whereas if you would have a larger object, you could make it move in different positions in different ways, so you could give it some internal structure. So now we can answer the why question. Even if the virus was red, and not all molecules absorb the green and the blue light in such a manner that only red will emerge, most molecules will just look invisible to visible light, and then you get transparent things. Like even the air, it is transparent to us. It's only if you have a very thick layer of air, you're watching mountains like kilometers away, miles away, you start seeing a very, very small hint of blue. And then if you watch the whole body of air around us, above us, then it starts becoming really blue. But in any case, even if the virus did have, for example, 3 benzene rings can give red color, did have such molecules which would give red, it wouldn't be red over here, another color here, it would just be one blotch, which is just a vague spot of a point-like object, and you wouldn't see any structure, any detail, colorless or otherwise. So we still know a lot about these viruses by other techniques. In particular, we could see the virus, but how can we do this? We can do this with electron microscopy. And the wavelengths of electrons can be much, much, much smaller, so you can see indeed all these spikes and the virus itself, but these electrons are colorless. So the Y is then, the color is given by humans. And that may start out very typical if you have a structure which is complex with subcomponents, then people like to give them pseudo colors, so they can say, look, this thing starting here and ending there, that's a spike, let's give it a color so we can immediately see it, and let's give it a red color because it's very conspicuous. And then the people who started making the magazine articles and the news, they could use the red color for another reason. Because red is the color of danger, it's a color of respect. So you would give the virus much more respect than if it was, for example, baby blue or pink. And everybody can have his opinion about the virus, but my little piece of wisdom is, remember that this is a poison, and it's a poison which self-replicates, which multiplies in your body. So I would rather be safe than sorry and have it outside. And if you make the virus look aggressively red, then people will maybe have more respect for it. So this was a fitting and also in tune with the times introduction to the video we have made about the meaning of the color red, not just in this particular example, but in many other examples. So you're welcome to watch it and learn something for when you want to use the color red yourself.